Our first look at bonding as either a sharing of electrons or a transfer of electrons helped answer the question of why bond and even got at the idea of how electrons form bonds. Now we need to look at the bonds themselves and consider more details than just is it covalent or is it ionic. The first type of bond we will consider is one we haven't mentioned before, the metallic bond. Metals don't form compounds with one another, but they can be mixed together to form alloys like bronze, brass, and stainless steel. This is the same type of bond that occurs between individual atoms in a pure metal sample like copper. Because metals have very few valence electrons, there is not really any way for the atoms to achieve a noble gas electron configuration. Instead, the valence electrons are shared between all of the atoms in an electron cloud that spans the entirety of the metal sample. The positive ions created when the valence electrons began to wander around are locked in place, while the valence electrons move between all the ions in a large electron cloud. The total number of protons and electrons is still the same, so the metal piece itself has no charge. This freedom of movement of electrons is responsible for many of the characteristics we associate with metals, like ability to conduct heat and electricity, ability to be bent, ability to be drawn into a wire or hammered into a sheet, or even the shiny appearance of metals. Covalent bonding is the situation resulting from the sharing of electrons. This occurs between two nonmetals as a result of the small difference in electronegativity, and this is the type of bond present in molecules. You learned in Chem Activities 21 and 22 that sharing electrons does not always mean equal sharing of electrons. Let's compare the covalent bonding in hydrogen to the bonding present in hydrogen fluoride. H2 is an example of a nonpolar covalent bond created when the electrons are shared equally because the atoms involved have the same electronegativity. Notice that the electron cloud is equally shared between the two hydrogen atoms, with neither hydrogen atom having a larger electron cloud than the other. This type of bonding will occur anytime you have one element bonded to another atom of its own kind. By contrast, the hydrogen fluoride bond is an example of a polar covalent bond. This is created by an unequal sharing of electrons, and this unequal sharing of electrons occurs when the more electronegative element pulls the shared electrons closer to itself. The partial negative charge, right here, ends up on the element with the higher electronegativity, and the partial positive charge, right here, ends up on the element that has the smaller electronegativity. This partial charge situation can be represented either with lowercase deltas, as we see here and here, or with an arrow that points toward the more electronegative element, or toward the element with the partial negative charge, or the more electronegative element. The little hash on the end of the arrow here will help you remember which direction the arrow should point. Remember that partial charge is a measurement of how unequal the sharing of electrons is in a polar covalent bond. Remember that the partial negative charge always goes on the element with the higher electronegativity or the higher average valence electron energy. And the partial positive always goes on the element with a smaller electronegativity or the smaller average valence electron energy. Also remember that as the difference in electronegativity between the two elements in the bond increases, the value of the partial charges increases as well, and those larger partial charges indicate that you have a more polar bond. Ionic bonds are simply a very extreme case of polar bonds where the electronegativity difference between the atoms is so large that the unequal sharing of electrons essentially is best described as a transfer of electrons from one atom to another. Ionic bonds are characterized by a very large electronegativity difference between the atoms, such that electrons are transferred from one atom to another, creating ions. And the bond that holds these ions together is the electrostatic attraction between positive and negative ions. As we think about this, let's consider the bond that results between sodium and chloride. Sodium is an element with one valence electron and a very small electronegativity. Chlorine has 7 valence electrons and a very large electronegativity. Because the electronegativity difference between the sodium and the chloride is so great, these two elements can't really effectively share the electrons, but rather the electron from the sodium ends up being essentially transferred to the chlorine atom, resulting in a positively charged sodium ion and a negatively charged chloride ion. The positive and negative ions are then held together by an electrostatic attraction. When this type of bonding occurs, you end up with a situation that involves building a three-dimensional structure of alternating positive and negative ions, and the smallest ratio of ions in this three-dimensional structure is called a formula unit. Back at the very beginning of this class, I gave you a simple rule about chemical bonding. I told you that two nonmetals together will form a covalent bond, and a metal with a nonmetal will form an ionic bond. At the time, you didn't have the background to understand why this was the case, so you simply used the rule. But now we can look back with our understanding now and understand why the rule is the way that it is. We have now learned that if the difference in electronegativity between two elements is high, it's because those elements are far apart on the periodic table. For example, a metal and a nonmetal. And our very simple rule was that if you had a metal and a nonmetal, that would result in the formation of an ionic bond. We now know that if the difference in electronegativity is low, that must mean that the elements forming the bond are close together on the periodic table, or are both nonmetals. And we know that this small difference in electronegativity is going to result in a covalent bond. The other thing you can see now is that bonding is not a black and white situation. The characteristics of a bond depend upon the difference in electronegativity between the elements involved. If we look at the possible differences of electronegativity between elements in a bond, That possibility ranges from there is no difference in electronegativity at all the way up to the largest possible difference, which would be francium and fluorine bonding to one another, where you end up with an electronegativity difference of 3.28. The obvious breakpoint to separate ionic bond from covalent bond would likely be in the middle, or right around 1.64 for an electronegativity difference. But if we look at this in terms of what we know about polar and nonpolar and ionic bonding, we can see that our nonpolar covalent bonds are on the far left end of our continuum. As the electronegativity difference becomes greater and greater, our bonds become more and more polar. And as that electronegativity difference becomes even greater still, our very polar bonds can no longer be described as a sharing, but are better described as an ionic bond in which a transfer of electrons has occurred. In the region right around an electronegativity difference of 1.64, the bonds really have characteristics of both ionic compounds and covalent compounds, and so we're going to have to resort back to simply looking at what type of element is involved to decide what the primary characteristic is of the bonds. For our compounds created by only nonmetals, the primary characteristic of their bond is going to be covalent. Although as the electronegativity difference becomes larger and larger, those covalent bonds are going to have small bits of ionic character. Once we get to larger electronegativity differences, and we're looking at compounds formed from metals with nonmetals, those compounds are going to be primarily ionic in character, although if the electronegativity difference is close to about 1.64, those ionic bonds are going to have some covalent characteristics as well.